much. Also, thank you to the organizers of this conference. I was last week at the summer school and I had a blast. It was an amazing time that I had. And I hope that the conference will be the same. Oh no, there's a little bit of connection problem. Okay, let's see. Yeah, thank you for introducing me and reading this long title out loud. I'm Jadwiga Wilkens. I'm a PhD student in Richard Kung's group in Linz. This is my favorite group picture because we are called the quick sloths because our name of the group is Quantum Information and Computation at Kepler. And Richard was so kind to be our sloth in this group picture here. And I just shortly about myself, I did my bachelor's and master's thesis at Jens Eisert Group in Berlin. Then I went to Abu Dhabi for a year to work with Ingo Roth, and now I'm a PhD student at Richard's Group. And the project that I will talk about today is actually a collaboration of lots of people. So Richard and me in Linz. Then we have Abu Dhabi people where Leandro Arlita he's the director of the Quantum Institute. He will be here this week, I think. Then we also have collaborations in Singapore and also, very importantly, industry partner, Rigetti, which are an amazing team to work with. And I'm very happy to show some results in the end from their superconducting qubit platforms. And well, today we're here in Natal, and I'm very happy to talk about my current research with you. And I will start very slowly about what is a gate set. So a gate set that we will characterize in this talk together is just a collection of gates that you already have in our qubit. So give me a qubit. Please already do the work of calibrating the Rx pulse and everything. I don't want to calibrate any pulse levels, but I want to have a nice gate set, for example, the Clifford gates. Then I can tell you how well is this gate set implemented in your device. And I always think about in how much information do we gain from our protocols and how much work do we need to put into that actually. And the most, well, easy protocols are just telling us one number about our gate set. How well is it implemented? It tells us, for example, the effective depolarizing strength of our noise that comes with this gate set. Standard randomized benchmarking, effective depolarizing strength that we get out of there. There are other protocols like filtered RB that Markus Heinrich developed, something like mirror RB. This list is not exhaustive, but they give us one number to tell us how strong is the noise in our gate set. Then we can also infer more information, structure information. For example, is there crosstalk in our chip using these very easy protocols? How coherent is our noise with unitarity benchmarking? Cycle benchmarking tells us about our Pauli words of our noise. So there's lots more to learn. Then there's something in the middle called RB tomography. And this is actually the workhorse a little bit of this talk. I will talk about this. I didn't develop this, but we use this protocol. And then on the other spectrum is something like gate set tomography, where we need to know, where we can get to know everything about our gate set, which maybe in some cases a little bit too much, and it is not very scalable. This is mostly done for single and 2 qubit gate sets. And then also something like Hamiltonian learning can give us much more information about our underlying system. So in this talk, we will use RB tomography, and I will show you a little bit how this can be derived from these protocols. And then we can show that having this information from RB tomography, we can also infer information about all the other protocols about the structure of our noise. And I find that very exciting. So let us start with standard randomized benchmarking. What is it? Why do we need it? Why do we love it? It's a very easy protocol. You start in the 0 state, you draw random gates from your gate set. I will use as an example always the Clifford gates. So you draw random Clifford gates, M of these. You apply them in your noisy qubit. Then in pre-processing, you need to calculate the one inverse gate that should, in theory, bring you back to the 0 state and do a computational basis measurement. You do this m many times. You should gather a lot of statistic for every sequence length, and then you aggregate it per sequence length. And what you will see is that your qubit will slowly decay. So you will mix into the 1 state, not always end up, oh no, in the 0 state. What is happening? This did not happen before. Maybe I should. It's there again? Yeah, I'm sorry. All right. When you fit the signal with depending on the sequence length, you will get out these parameters A, Z to the power of n plus B. A and B absorb your spam errors, which is very nice because it's the state preparation and measurement errors that you don't want to care about. It's really the gate set. And then this Z is your decay parameter. The closer to 1, the better. So now what is happening in experiments, people are counting how many 9s are in the end, and then you have to brag about how many 9s you have in your average gate fidelity, which tells you how close is your error channel to the identity. The closer to the identity, the better. Now, I will always omit all these things around that. So when I write these protocols, it's always implied we have sequence lengths, and then we have a lot of shots for these sequence lengths. There's another protocol, the filtered randomized benchmarking, where you can do the inverse in post-process, which I find super cool. We will lose a little bit of sample complexity, but that doesn't matter. So if we now do the inverse gate in the post-processing scheme, then we first see a little bit of a weird signal, and to fix this signal that looks a little bit weird, we need to know how our channel representation looks like. And I always love to think in tensor diagrams. So our general, if we apply unitary, this is the action by conjugation, u row, u dagger. This can be written with our boxes here. And then we can vectorize our channel such that we can also represent it as a matrix. All right. So always when you see a curly u, then you know this is a channel representation of this gate acting as in conjugation. And then if we would choose a basis, the Liouville computational basis, for example, you don't see any structure. But if you go into another basis, the Pauli basis, then you see that your representation decomposes into irreps, irreducible representations, the one block, and then all the Pauli blocks. And knowing this structure that is inherent from this representation here, we can now interleave a predictor that brings us into the space that we care about, and then we would see a decay parameter. We could get that again. So again, the important thing is this average gate fidelity here. And now people thought about, what if I have more of these average gate fidelities? What if I can also see how close is my error channel to the X gate, or to the Y gate, or to the Hadamard gate, right? And then having this list of average gate fidelities of, let's say, all the overlaps of all my Clifford gates, then people in 2018, Wood et al. Could together with Richard, proved that having a unitary tree design, you can express these kind of channels as an affine combination of the average gate fidelities of your unitaries, weighting the channel itself. Super nice result. That means that if we have access to all these average gate fidelities, we can reconstruct the error channel that happens in the middle of our gate set. Then Kim et al. Came and proposed, actually even before this paper that I just said, an experiment that does that. Namely, for the Clifford gate, for example, a Clifford gate set, we have 24 randomized benchmarking experiments. And in each of these experiments, we do a normal randomized benchmarking, but we interleave these probe operators after every gate. And if we do that, then this decay that I showed you is not just the average gate fidelity with the identity, but with this probe operator that you actually interleave there. So this gives you access to all of these average gate fidelities. There's a problem. First of all, these probe operators can be noisy. And second of all, this would yield 24 experiments, but if we go to the 2-qubit regime, then we need to probe in all the different combinations of my 24 Clifford operators. 24 to the power of 2 is 576. We would need 576 experiments to get all the 2-qubit fidelities. That's too much. This is not feasible, so people kind of dropped it. And then Helsen et al. Showed that we can do everything in post-processing. We can have one huge experiment, and then in post-processing, interleave all these operators that we need, 1 body, 2 body, whatever you want, with the praise that we have a high sample complexity, but let's skip that for a second. And then we also need to project into the right space, and then we can infer all these average gate fidelities from one single huge experiment. And I find that super cool that this works. And the protocol goes as following. We have one huge experiment, right? It's simultaneously on all qubits, layers of random Clifford gates, and then we gather from one shot, so one single huge layer with m of these layers is one gate set, given that you did a computational basis readout. So this u, and then the bits that you get is one gate set shadow. And then what happens, because you have these local Clifford gates that twirl away your noise, is that you actually twirl away lots of information. So what we actually see is a block diagonal structure that happens now. And this block diagonal structure, okay, I will just keep talking. This block diagonal structure tells us that we can only see, after this twirling process, quantum noise that is stochastically correlated. So we cannot see entanglement noise. We are twirling this away. But every single qubit quantum noise that is stochastically correlated between different qubits, this information we can resolve. Ooh, oh God. Did it work? Okay, cool. Thank you. So this is what I mean with this irrep. I will give a, yeah, just put erlauben. Yes. I did not. Let's take that risk. So then I will give an example how this block diagonal structure looks like, but we are losing information here, but not all of the information, and we actually can gain a lot back. So after having this huge experiment, what we need to do is we need to filter the data. And now, this is a bit technical, but for each single qubit marginal, we need to interleave, for every gate set that we get, we have to interleave 24 of these prop operators, and then for each two-body system, we need to interleave 576 prop operators. So we blow up our database by a lot. Doesn't matter, we can just fry our computer. And then we need to, again, aggregate per sequence length, per prop operator, and then we get these decays, and these decays tells us the average gate fidelity of the interleave prop operator with our channel. Then we can use this equation that I just showed you to reconstruct your whole channel, and I just want to give you a little example of how that would look like with 3 qubits. So let's say that we have a 3-qubit experiment, and then our 2-body marginal channels would look like this. So for every qubit pair, we can reconstruct this Pauli transfer matrix, where this block here encodes the mixture, so the crosstalk kind of the 2 qubits. Then the first index here is indexing this block, and then the second index is actually indexing the first block. It's how we defined our basis anyway. So if you would not do now this huge experiment, then you can, in post-process, marginalize the data. And first of all, our 1-to-1 map is always 1 because it's CP trace preserving, so I always set that to 1. And then if we look at the first qubit, we marginalize the data for the first qubit. We could reconstruct these blocks here. The second qubit is the blocks that are next. So always, yeah, I mean, I will not explain too much about the position here, right? And then the third marginalization for the third qubit would then give us these single qubit blocks here. And then if we look at all the 2-qubit marginal channels, that's very slow. You can do it. Yes. So this would be the 2-qubit marginal channel that we reconstruct with this data here. And then the other 2-body terms, we will reconstruct the other big blocks here, 9x9 blocks. All right. And then in theory, we could also reconstruct the 3-qubit body marginal, but the sample complexity is very bad. No, I skipped. So we don't do that normally, but you could do that. Okay, so this is how we reconstruct. Then we output our channels, these pretty Pauli transfer matrices. Now we saw that we can actually denoise these because this is a lot of short noise that we see here. You could denoise it with the semi-definite programming that Daniel talked about last week in the lecture. What we saw here is that gate-dependent noise can lead to non-positive Chi matrix representations, which is nice because then we can see, okay, negativity means that there's something going on in the gate-dependent noise. So that's why we normally now don't do that. Well, I don't need Wi-Fi. That normally we don't do that, but if we know that our channel is not gate dependent, we could denoise that, and then we analyze all these Pauli transfer matrices. And what could we analyze with it? Well, we could stare at the Pauli transfer matrix and then look at the X is being mapped to the Y, so this has to be a Z error. We see if it's diagonal or not diagonal, if it's only depolarizing, if it's only a Pauli channel, you know. We can just stare at it very closely and check how it's doing, but it's not very productive. So what we did now is we implemented different post-processing protocols on what we can do with it. For example, we can now get out the effective depolarizing strength of this channel. It's just the diagonal, what the standard IB protocol would give us to. We can also infer that. We could check the unitarity, how coherent is my noise. Then on the 2-qubit level, we can check the so-called addressability. So how well is the two block explained by taking the product of the first and the second block for the addressability, and then also the correlated unitarity. And then we went a step further and said, okay, Pauli transfer matrices are a bit boring. We can go to another representation, namely the error generator rates. And that's a bit technical, but for small Markovian errors, we can always say that our error is generated by an L, our error generator. So taking the logarithm of that channel then gives us the generator L. And the people who wrote that paper now saw that there are 4 different sectors: the Hamiltonian sector, the stochastic sector, the stochastic Pauli sector, and the active sector. It doesn't matter, it's a bit technical, but they all refer to different noise types. And this is a bit more informative than just staring at Pauli transfer matrices. So we took these sectors and then split them into weight 1 and weight 2 generators, and then built this wonderful vector out of our Pauli transfer matrix, where then we can see more structured information about our noise. And we also in this project defined an average case correlated noise number that just is the L2 norm of all the weight 2 error generators. All right. So this is what we can do with how we could analyze our channels now. And of course, this was not exhaustive. You can do a lot more with it. You can do so many things. I don't even have time to list them probably. But let's now look at some results that we have with our industry partner, with Rigetti. And what they managed is, I mean, they implemented this many, many times now, but one of my favorite data sets is a data set with 36 qubits. They go up to sequence length 32. And of every sequence length, they managed to get 10 million shots. And this only took a few hours. So they managed to implement everything in the FPGA, so in the lowest level, and made it run so fast that I don't even know how they did that, but it's really, really cool. And with that, we could get a lot of data sets and look at different groups and different error models. It's really, really amazing. And what we did on top, what they managed on top is implement some synthetic noise. So they made a little hide and seek game with us. So the experimentalists were hiding some synthetic noise that they knew very well how it looks like. The stochastic mixture of either doing nothing or a little over rotation on 2 qubits. And then we, as the theorists, post-processing team, had to kind of find these noise channels, and it worked. We found them. So we kind of showed that this protocol is working well. And what I do is, given this huge data set, it takes very long to be post-processed, but let's say that I have a very good computer. So first I reconstruct the single qubit marginals. We have 36 of them. Then I stare at the Pauli transfer matrices and I'm like, oh, qubit 26 and qubit 27 seems like they're not doing so well. Also qubit 35 has kind of a strong noise, and I always subtracted the diagonals so we can see the off diagonals. But you can see already, this is not just diagonal noise. It's not just depolarizing or not just Pauli noise. There's something going on in the off diagonals, which means that there's coherent errors going on. So this is already a first result where we're kind of blown away to really see these maps, because nobody else kind of saw them in real life from real data, which I find already super cool. And then we used these single qubit maps to look at different performances. So the effective depolarizing strength, the unitarity of these channels. I also look at the negativity. So the sum of the absolute values of all the negative eigenvalues of the chi matrix. So how negative is the chi matrix representation? And we saw that this is kind of linked to gate dependent noise, which is also super cool. And now we can see already, so the green qubit series seem that the noise was interleaved there, so we should not trust these values so much. But you see that, for example, the negativity, so these red dots here are pretty high, so we probably have some gate-dependent noise here. And also the depolarizing strength here, I saw that the qubits after that, the non-unitarity is kind of following that we also expect. So we see some fingerprints where we're like, okay, that everything looks good, and then we can use this to really look at our noise in the single qubit regime. Also, the spam errors are cool to look at here on the right, that drop out of the randomized benchmarking decays that we fit. Okay, good. What we also did is look at the error generators, because for each Pauli transfer matrix, we can now go into this vector that I showed you for the 2-qubit case, but we can do the same for the 1-qubit case. And then we can build this matrix of error generators, where here on the y-axis, we have now each qubit. And then the x-axis tells us the strengths of each of these error generators. And we can see here that the most strong error generator rate is the Hamiltonian Z. So there's some coherent error going on pretty much in this Z direction. So the qubits have a coherent Z error. And not enough. We can now treat this matrix as a data matrix. and can perform a principal component analysis of this data matrix. And I would just brush over this, but I find that super cool. So in the end, we treat this as a data matrix with our features being the error generators and our indices being our experiments being the qubits. And then we can cluster our first two principal components here. And what we saw is the outliers are our most noisy qubits here, 25, 35, 27, and 26. And then I also saw that the cluster found all the synthetic qubits, so where the noise was interleaved in a synthetic fashion. And I found it very cool that we just found that, it popped out of this PCA analysis. Then after going to the single qubit channel, of course, we also have to look at that's the most interesting part, right? The 2-qubit maps. And I only show you the nearest neighbor Pauli transfer matrices because all of the pairs would be around 600 Pauli transfer matrices, and I did not want to overwhelm you. So now I only show the nearest neighbor Pauli transfer matrices, and you can see here in green the synthetic noise channel, and they're almost non-existent because there are other errors that are actually ramping up our color bar here. So we can see that there's a lot of noise going on in some qubits. But again, staring at Pauli transfer matrices is not very productive. So we should stare at the error generator matrix, which maybe is also not that productive because it's a lot of data. And again, this is only the nearest neighbor, okay? We have this matrix for all of the 600 pairs. But what we already can see is that we can see a bit more structure here, right? Like it really seems that qubit pair, I will read it out because it's too small, 24 and 25, have something going on here that the other qubits do not have. Also marked in green, we have our synthetic noise, and it seems that they are always the same. So it's already cool to see that. And then using all the data that I just showed you, we can now look at the crosstalk metrics. So again, we also can do this for all the pairs, but I only show you for the nearest neighbors. And here we plot 5 different metrics. The addressability, meaning how well can I address each single qubit in this big experiment. Then the correlated unitarity, how coherent, how good is the coherence description of the single qubit channels versus the big qubit, the 2-qubit channel. Then we also look at the so-called worst case correlated noise strength and the average case correlated noise strength. And then also in purple, the negativity, again, telling us if there's some gate-dependent error going on. And as you can see, the addressability, it's kind of down there. It's not very big. So if we would only run this addressability experiment, then we would actually not really see that there's crosstalk going on because it only looks at the diagonal of our Pauli transfer matrices. Also, the correlated unitarity, it bumps a little bit up, but it actually follows a little bit the addressability. So these orange thing, if you cannot see them, then they are somehow either under the blue ones or they are grayed out because they're equivalent to 0. So these 2 metrics are nice to look at, but they don't really tell us the whole story, right? So if we look at this worst case and average case correlated noise, we can really see that they give us a bit better picture of the crosstalk going on in this chip, and we can see that. So the average correlated strength is the red ones, and we can see that in the last qubits here, the addressability is like, there's maybe a bit crosstalk, but we can see that actually there's a lot of crosstalk going on between these qubits, looking at this new metric that we implemented in this paper that will hopefully be published soon. And also, again, the negativity tells us that there's a lot of gate-dependent noise happening. Yes. And with that, I would like to finish and tell you again how awesome it is to look at these retomography scheme and then make a crosstalk analysis of it, because we can really do a lot of things with this just Pauli transfer matrices, not just what I just showed you, but in the paper that will come out soon, you will see a whole report of plots and tables and analysis that you can do with this whole protocol in a spam robust way. And with this, we need to now look at these little plots coming up. Yes, with this, I would like to thank you for your attention.
Thanks for the nice talk. Do we have questions from the audience? Yes.
Yeah, thanks, Jadwiga, for a nice talk. So has Rigetti done anything with that information? So have you looked at the chip and found that qubit 25 or what it was sucked a bit, or what happened?
Yes. So for example, qubit 26 and 27 had one of the biggest crosstalk, but they are not nearest neighbor nor next nearest neighbor. They don't even share a line of readout or anything. And before, their protocols only looked at next nearest neighbors, so they were not even aware about this crosstalk. So yeah, they already used that information. And yeah, I mean, probably you can now do some optimization algorithms with an elder meet or something. But yeah, yes.
I actually had a related question. So what is the topology of their chip? Is it like, it's like a kind of like a tree or like a 1D thing? Or?
Yeah, no, it's a square. I wasn't sure if I'm allowed to show you the letters because I couldn't find it online.
Okay.
So maybe it's not, but it's a square and everything is connected. So it's 1 to, I don't know, 6 by 6. Yeah, 6 by 6. But then in the middle, qubit 26 and 27, there's one gap between these and there's no line that they share.
I see.
Yeah.
Thanks. Other questions from the audience? Yes, Michel. Let's find out. After a weekend in Pipa, I'm good at going upstairs.
Thanks, Jadwiga, for a nice talk. I maybe didn't catch that point because you mentioned that the protocol is spam robust.
Yep.
So, but does it relate some crosstalk in readout noise? Because like for those superconducting devices, let's say we some time ago observed, like together with Asha actually, this type of effects, and readout noise is quite strong in superconducting qubits.
Yeah, good question. I think it is, I mean, it's measurement robust, right? So I think it is also measurement robust when there's crosstalk in the measurement lines. I mean, because most qubits share a measurement line, right? Like there must be some crosstalk between them. But I'm pretty sure, I mean, randomized benchmarking, standard randomized benchmarking is also robust against crosstalk in the measurement, right? So I do think that this is robust against all of this. And we did see that the spam error of some qubits was really high. So the optimal value would be 2/3, so 0.666 period. And one of them had 0.2.
So can you do like using the same data, like map the readouts noise as well, maybe?
Good question. Maybe we could kind of define an addressability for the spam error. That's actually a good idea. We should check that out. Thank you.
Thanks.
Maybe we have time for one more quick question. Yeah.
Thanks for the nice talk first. Hi. My question is there a way in your method to quantify how non-Markovian the noise is? Or, I mean, that's somewhat approximated away, I guess, if you go to the generators. But I guess like for the experiment, you have some percentage of leakage, for instance, and then Markovianity.
Yeah, very, very good question. So your question is about leakage and non-Markovianity. Yeah, so leakage is an ongoing research question, but non-Markovianity, we are pretty sure that, I mean, normally these are small effects, and we are pretty sure with this twirling of this local Cliffords, we probably twirl away all the information. So what we could look at is at these, what I showed you, these decay plots. If you maybe have something a bit unusual in there, so maybe it does not really follow a decay, but maybe 2 or 3 decays that overlap each other, then this would mean that there could be a non-Markovianity. But again, we try to infer that a little bit, and it's impossible to tell really. I think it's really everything is kind of twirled away with this twirling process. But I'm happy to discuss that. I don't have a very good gut feeling about that.
All right, so maybe let's thank the speaker again.